So now that we've discussed kind of the bookend mechanisms that the Java Streams framework provides to split things up using splitterators and combine things using collectors, let's talk about other ways in which the Stream framework is designed internally in order to build up and construct a stream. So recall we've talked before about the fact that intermediate operations in a stream are lazy. And what that means is they don't actually do anything until a terminal operation is reached. But what does that really mean? How does that work? And what's the implications of this particular lazy action? What it means is that when your source code is converted into the runtime equivalent, the byte code or the ahead of time compiled code, or whatever the representation is that your implementation of Java uses to create something that will execute at runtime, those intermediate operations don't actually do something right away. Instead, what they do is they basically work as factory methods that create a linked list of source and intermediate operations. One element, one node in that linked list for each of the stages in the pipeline. So you can see here if you have .stream, .map, .filter, .sorted, all those things turn into nodes in a linked list that's created as your program executes. So it's actually building this internal data structure on the fly as your code is executing, as your code is running. And if you want to learn a little bit more about what happens here, take a look at the link at the bottom of the slide, which talks about how this stuff behaves. Now, what happens is each of these stages that are built is described by internal data structures, which are basically bitmaps that keep track of flags that are set as this pipeline, this linked list is being built on the fly as your program starts to run the streams code. And the flags, we'll talk about these flags in a second. The flags include sized, distinct, sorted, and ordered. And these are basically a subset of the flags that can be defined by a splitterator. So if you have a splitterator, for example, like Arraylist or linked list or hash set or so on, those different collections have splitterators, and those splitterators set flags to indicate properties of the source of the stream. And the flags we're looking at here are basically a subset of those flags. So let's talk briefly about each of these flags. One flag that can be set is sized, and that means that the framework knows how many elements there are in the source of the stream. For example, an array list, a hash map, a linked list, a tree set, those are all collections where we know the number of elements at the beginning. There are other kinds of sources for a stream that are not sized. A good example would be the iterate method or the generate method, which is defined on a stream. Those will create non-sized streams. Another property, another flag is called distinct, which says the elements of the stream are non-unique. So for example, if something is originating from a set, then we know that it's going to have unique elements because sets can't contain any duplicates. Conversely, if it's something like an array list or a linked list, then those can have duplicates. So distinct would not be set if the stream comes from those types of elements. Another property is sorted, which means that the elements of the stream are sorted in so-called natural order, either ascending or descending. And again, some data structures, some stream sources will be known to be sorted. For example, if you have something that's going to be a tree set, then that's known to be sorted. Conversely, an array list may or not be sorted. A hash map probably is not sorted. It's hashed, not sorted. And then the other key bitmap that's a characteristic here is the ordered characteristic. And that means that the stream has a meaningful encounter order. That means that someone cares about element 0, element 1, element 2, element 3 in that order. So certain sources of streams, like array lists, have encounter order that is meaningful. Conversely, if you have something like a hash data structure, like a hash set or a hash map, that doesn't really have meaningful encounter order because they're hashed to whatever they're hashed to, and it's not going to be relevant in terms of the order in which they come through. So those are some of the characteristics that can be set. Now, you might ask, who the heck cares about this stuff? Well, this is actually quite interesting, and I'll explain why in a second. But before I tell you why and how these things are used, let's talk a bit about some mappings of these bitmaps onto different common collections in Java. So, for example, the Arraylist collection is sized, because we know how many elements it has, and it's ordered because it has a relevant encounter order from beginning to end. But we don't know necessarily if the elements in an array list are sorted, nor need they be distinct. They might be in some given circumstance, but just knowing that something's an array list doesn't tell us if it's sorted or distinct. There's also other types of collections like hash sets and tree sets. A hash set is sized and it's distinct because it's a set, but it's not ordered in the sense we don't know what the ordering is. There's no meaningful encounter order because hashing just scrambles up the input any way it sees fit based on the hash function. And a hash set is not sorted. In contrast, a tree set is sorted and it's also ordered because it's sorted, and it's distinct because it's a set and it's sized. So that's an example where all the different flags in that bit mask will in fact be set. As I mentioned before, certain methods on a stream, like generate and iterate, will create streams that are not sized. So we won't know how big. And of course, they also aren't going to be sorted. They may or may not be distinct, right? So these other properties would not be set for those sources of a stream. Now, once you've got the initial source of the stream properly configured with its bit mask, then each of the intermediate operations that are in the stream will affect the flags. And so let's take a look at some examples here to make this more concise. So if you have a map operation in the stream, then that's going to clear the sorted and distinct flags because, of course, map can make arbitrary changes to the values, so they may no longer be sorted, and they may no longer be distinct. But it still keeps the sized flag set because it still knows it's going to have as many elements coming in as coming out. In contrast, the filter intermediate operation doesn't change the values. So if it was sorted before, it'll still be sorted. If it was distinct before, it'll still be distinct. However, filter clears the sized bit because, of course, there could be fewer elements coming out once we apply the filter. Likewise, the sorted intermediate operation keeps sized because it doesn't change the number, keeps distinct because it doesn't change the value, but it adds the sorted flag. So these are just examples of how the intermediate operations can affect the meaning and the behavior of the stream. Now, as the linked list is being created at runtime, the flags at each of the stages in that linked list are updated as the pipeline is being constructed to keep track of what's been set and what's been cleared. So the flags for a previous stage, for example, starting with the source, are combined with the current stage's behavior, and then that derives a new set of flags for that current stage. And that behavior propagates down through the elements in the stream. Why does this matter? Well, the reason this matters is because it makes it possible for the streams framework to apply some very clever optimizations, much in the same way that if you have something like a query optimizer for a structured query language or SQL query, then it can go ahead and simplify that query in order to do less work because it applied some optimization. Same basic kind of idea. It's also another way of looking at this is one of the benefits of using declarative properties as opposed to imperative, because it provides really good opportunities for optimizations. So here's a very simple example. If you have the source of a stream be a tree set, then we know that the elements are going to be sorted by their very nature. So if you go through and you convert that tree set to a stream, you know it's sorted. If you apply filter, you know it's still sorted. And then if somebody was sort of accidentally to put sorted in there as an intermediate operation, the streams framework would go, aha, there's no need to do sorting because there's no way that this stream is not already sorted by the time it gets to that operation. So it could go ahead and optimize away the call to the sorted intermediate operation very cleanly and very cleverly and very optimized and optimally in order to be able to get a shorter amount of processing because it knows something semantically about the elements in the stream and how they all fit together. So that gives you a quick overview of the way in which streams are constructed. And of course, when the terminal operation is hit, as we'll see shortly, that's what's going to set all the wheels in motion to actually begin to execute the contents of the stream. But we'll talk about that in our upcoming lesson.